Okay, so what I want to do tonight is to show you how to expand a binomial. For instance, let's say that I have something like x plus 3 squared. Now, that's not a difficult one. X plus 3 squared, we all know, if you do a double distribution, in other words, x plus 3 times x plus 3, you would end up with, when it's done, x squared plus 6x plus 9. That's not so bad. But then I might ask you to do x plus 3 cubed. And if I'm going to do x plus 3 cubed, I'm going to take the answer for x squared plus, or x plus 3 squared rather. This doesn't want to write. And I would multiply it by another factor of x plus 3. And so I would need to multiply the x by the x squared, the 6x, and the 9, and then I would multiply the 3 by the x squared, the 6x, and the 9. And so what I would end up with is x cubed plus 6x squared plus 9x plus 3x squared plus 18x plus 27. And when I combine like terms, I would get x cubed plus 9x squared plus a 27x plus another 27. And then let's say I ask you to do x plus 3 to the 4th. I would have to take this answer that I got from x plus 3 cubed and bring in another factor of x plus 3, etc., etc., etc. The question is, how many of these are you willing to do before you just say, forget it? Would you be willing to do x plus 3 to the 7th? Or x plus 3 to the 8th? Because I'm kind of guessing that most of you would not want to do that. So what I want to do is show you kind of a trick or a shortcut. There's actually a formula for this on the reference sheet. I'm going to show you 2 different ways to do it, and then you can decide your best way. So what I want to do is some expansions here, and I'm going to start out with x plus y, because I think it's easier when there's 2 variables to see what's happening. And x plus y to the 0 power is the first one that I'm going to expand, and we all know that x plus y to the 0 power is equal to 1. Then I'm going to take x plus y to the first power, and that would just be equal to x plus y. Then I'm going to take x plus y to the second power, and that will be equal to, when it's expanded, x squared plus 2xy plus y squared. If I go to the third power, I will end up with x to the third plus 3x squared y plus 3xy squared plus y cubed. I'm going to take it another one. X plus y to the 4th will give me x to the 4th plus 4x to the 3rd, y to the 1st. Don't really need that first power. Plus 6x squared y squared plus 4x y cubed plus y to the 4th. One last one here for you. X plus y to the 5th is x to the 5th plus 5x to the 4th y plus 10x to the 3rd y squared plus 10x squared y to the 3rd plus 5x y to the 4th plus y to the 5th. Now, if I have totally impressed you by the ease at which I did that, then good, because you should be impressed. No, just kidding. I'm going to show you a trick, and it's really quite simple. What we're going to do is we're going to look at the patterns that are happening here in this expansion. The first pattern that I'd like you to notice is that each of these rows, as I go across, okay, depending on the exponent to which I am raising this, so in other words, if it's x plus y, if I'm taking it to the second power, that the first term of the binomial is raised to the second power. When it's cubed, it's x cubed to the fourth is x to the fourth to the fifth, etc. And so the other thing is each of the coefficients on this first row all the way down is 1. Likewise, each of the coefficients on the last row all the way down is 1. Another thing that I'd like you to notice is that this first variable here, this x, which is the first term in each of the binomials, starts descending in order by power. So in the first term it's x to the fourth, and then in the next term it's x cubed, x squared, x to the first, and essentially x to the 0. But we know that x to the 0 or anything to the 0 is 1, so we don't bother writing it. But you will notice that in each of these particular rows, when it's x plus y squared, starts out with an x to the first, x to the second, x to the first, x to the 0. For the cube, it's x cubed, x squared, x to the first, x to the 0. In each of the successive rows across this pyramid, if you will. And so, with that said, the second term of the binomial, the y in this case, is going to increase by power as you go across. So this one here would be y to the 0, which again we don't write because y to the 0 is just 1. And then you have y to the first, y to the second, y to the third, and y to the fourth. And so in any given power here, for instance, the x plus y to the fifth, the second term of the binomial increases by power. So it's y to the 0, y to the 1, y to the 2, y to the 3, y to the 4, y to the fifth. The other thing that I'd like you to notice is that within any given term of that expansion, the two exponents are going to always add up to 5. 5, 1 and 4 is 5, 2 and 3 is 5, 3 and 2 is 5, 4 and 1 is 5, 5 and essentially 0 is 5. And you can check that out in any row. 4, 4, 4, 4, 4. For the cubic, it's 3, 3, 3, 3, all the way up to 0. That's just one of the patterns. The other thing I'd like you to notice is the coefficients that are actually on each of the terms as you go across this triangle. So what I've done is I've gone in and highlighted them in green. I hope it's not too hard for you to read. But you will notice here, on the first row you have a 1. On the second row, each of the coefficients are 1. On the third row it's 1, 2, 1. Then 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. Now, I don't know if you've ever noticed on the back wall, but there's something called Pascal's triangle on the back wall on the poster. And Pascal's triangle looks just like the coefficient piece of this expansion triangle. So I'm going to go to a new stage and I'm going to just put in Pascal's triangle. Pascal's triangle starts with a series of 1s, so it's a triangle of 1s. And then as you go to each successive line, the outside edges are 1, and the next term in between these two here comes from actually adding these two together. So my middle term would be 2, and then it ends in a 1. So there's always 1s on the outside of the triangle. The next row would be 1, and because 1 and 2 makes 3, and then 2 and 1 makes 3, and then 1. 1, this would be 4, this would be 6, this would be 4, and 1, 1, 5, 10, 10, 5, 1. And so again, if you look back on before the previous part of the video, these were all of the coefficients on that expansion, those expansions. So again, keep in mind, the way you get the 4 here is by adding these two numbers together. So they kind of sandwich like bowling pins, if you will. Okay. So if I was going to go to the next line, which would be the expansion to the 6th power, I know it starts with a 1 on the outside. These two together would add up to 6. These two would add up to 15. these two would add up to 20, these two would add up to 15, and these two would add up to 6, and then I end it with a 1. Now I can continue this for as far as and as long as I need to. We don't typically have to go higher than a power of 6, but sometimes they throw in some extra ones, and I'm going to show you another way to look at this triangle. So here's the trick, if you will. Let's say I ask you to take x plus y to the 4th power. The first thing I need to do is identify the degree to which I am expanding this, and that is the 4th power. And then I'm going to go to Pascal's triangle here, and I'm going to find the 4 in the triangle, and that's this row right here. So I'm going to highlight this row right here. Okay, and again, it's because of the 4. I need to find the 4 in the triangle. That means then that each of these are the leading coefficients to the 5 terms in the expansion. And so what I'm going to do is I'm going to just write them down. 1, 4, 6, 4, 1. You leave myself plenty of space because I need to put the rest of the terms in there. Then what I'm going to do is take the first term of my binomial, which in this case is an x, and starting with the first term of my expansion, I realize that the first term is going to have that x raised to the 4th power. And with each term as I proceed across, that power of x is going to decrease by 1 as I go all the way to 0. Then I'm going to take the second term of my binomial, which is y, and I'm going to increase, starting with 0, because remember, these have to add up to 4 right here. So it'd be y to the 1, y to the 2, y to the 3, y to the 4. I'm going to throw some plus signs in there. And then I'm going to clean up each term so that it doesn't look quite so sloppy. So this first term here, 1 times x to the 4th times y to the 0. Remember, y to the 0 is just 1. So that's just going to simplify to x to the 4th plus. The next term here, 4 times x cubed times y to the 1st, I'm going to simplify to 4x cubed y, plus this term will be 6x squared y squared. This one will be 4x y cubed. You could put the power of 1, but you don't need it. Plus, and then this last one is basically 1 times y to the 4th. And there I have my expansion. So here's another example. I'm going to have you do x plus 2 to the 5th power. And so again, I look at this here. I'm going to do it in red so it stands out. I look at this power of 5, and I go to my triangle over here, and I find the row with the 5. And so understand that something raised to the 5th power is going to actually have 6 terms. And so I start out with my coefficients, 1, 5, 10, 10, 5, 1. Then I'm going to take the first term of my binomial, which is x, and I'm going to raise that to the 5th, and then to the 4th, and then to the 3rd, and then to the 2nd, and then to the 1st, and to the 0. So I'm not even going to write it down on the last one. The second term of my binomial is a 2 here, positive 2, and so I'm going to, I can skip this one or write it down, it doesn't matter, 2 to the 0. Remember, these have to add up to 5. This will be 2 to the 1st, this will be 2 squared, this will be 2 cubed, this will be 2 to the 4th, and lastly it's 2 to the 5th. And then of course all of these get little pluses. Okay, and then it's just a matter of cleaning this up. So now, this first term, I have 1, I have an x to the 5th and a 2 to the 0, which is 1. So that's x to the 5th, plus. On the second term, I have a 5, an x to the 4th, and a 2 to the 1st. This 5 and this 2, because I have a number here now, not variable, they're going to combine to a product of 10. So I'm going to write this as 10x to the fourth. On the next one, I have a 2 squared here, which is 4 that will get multiplied by this 10. So that will be 40x cubed plus, here I've got a 2 cubed that's going to get multiplied by the 10. 2 cubed, of course, is 8, times the 10 makes 80, x squared. On the next one, this 2 to the 14th is actually 6, or 2 to the 4, I'm sorry, is 16. 16 times 5 turns out to be 80x plus, and then this last one is 2 to the 5th, which is 32. And there's your expansion. X plus 2 to the 5th power. Much quicker than if you were to do it the longhand, or the long way. So something else that I want to show you that's pretty cool about Pascal's triangle is the fact that this is also, or can be built through combinations. And so if I look at each of these rows, what I need to understand is that this row right here, for instance, this last row that I put down here, this 1, 4, 6, 4, 1, can be built by taking the combination of 4 things 0 at a time, combination of 4 things 1 at a time, the combination of 4 things 2 at a time, combination of 4 things 3 at a time, and the combination of 4 things 4 at a time. If you were to put these combinations into your calculator, each of these would actually match up. Combination of 4 things 1 at a time is 4. Combination of 4 things 2 at a time is 6. Combination of 4 things 3 at a time is 4, etc., etc. So if I wanted to build the next row, again, I could do my adding and say 1, 5, 10, 10, 5, 1, which is great if you have Pascal's triangle started. Or I can look at this as the combination of 5 things 0, combination of 5 things 1, combination of 5 things 2, combination of 5 things 3, combination of 5 things 4, and the combination of 5 things 5. Now the advantage to this and understanding this piece of it is that if I asked you to take an expansion to, say, the 12th power, they're not going to ask you for the whole expansion. They might ask you for a specific term. Like they might say, find the 4th term of the expansion. So the 4th term would, if it was this to the 5th power here, the 4th term would actually be, this would be the 1st term, the 2nd term, the 3rd term, the 4th term, the 5th term, and the 6th term. So the 4th term would be the 4th one in, and this is where I would start. Okay, so let's say I asked you to do x plus 3 to the 12th power, and I wanted you to find the 4th term of that. Okay, so I would know then that the first term would be the combination of 12 things 0 at a time. The second term would be the combination of 12 things 1 at a time. The next term would be the combination of 12 things 2 at a time. And the 4th term would be the combination of 12 things 3 at a time. I can put that in my calculator and figure out the actual starting coefficient without having to build Pascal's triangle all the way to that 13th row, which is basically what it is. Okay. So with that being said, so what I could do then, if I finish this, is 12 choose 3 turns out to be 660. I get a pen. 660 is the starting coefficient. I'm going to take the first term of my binomial here, which is x, and raise it to the, now I have to figure out the power, but as long as you can count backwards, this is easy. So in the first term, the x would be raised to the 12th, and then to the 11th, and then to the 10th. So by the time you hit the 4th term, it's to the 9th. And then the next term in my binomial is a 3. And knowing that these two numbers here have to add up to 12, I can tell you that this would be raised to the 3rd power. So what I end up with then is 660 times x to the 9th times 27. And when I multiply the 27 times the 660, I'll actually get the coefficient on this term. I don't have a calculator with me right now, so I'm going to leave that to you. But that's how I would do that. So I think this video has gotten long enough. I just wanted to get these in your notes for you. Tomorrow what we will do in class is we will look at the formula that they give you on the reference sheet and see how it compares to Pascal's triangle method. Okay, have a good night.